Good morning. This is still the lecture series on the Klein's Organic Chemistry textbook, second edition. Failed to charge my iPad over the weekend, so I'll just be using the phone and the whiteboard here for presenting the information. This is section 20.4, and we're going to focus on introduction to nucleophilic addition reactions. First thing I want to do is talk about the reactivity of carbonyls and compare formaldehyde, acetaldehyde, and acetone. So if we can draw acetone here, we see it's a fairly polar compound. We have a carbon-oxygen bond there, so there's a polarity pointing up. Acetone is water-soluble. It's much more polar than we would otherwise expect from first principles. And the reason for this is because we can draw a resonance structure. And now we have this Zwitter ionic compound that's polar, it's charged. It's not a good resonance structure, okay? So if we average these two, we're gonna get the overall resonance structure hybrid for acetone. It might be, 95% this and maybe only 5% that. Why not so much this? Because there's no octet on carbon, there's less pi bonding, there's charge separation, right? Opposites attract. So that's a terrible resonance structure. But it accounts for 5%, let's say, for the properties of acetone that allow it to be water soluble. This is a much more polar substance compared to this because you can definitely see the charge separation there. So acetone does have some of this character that allows it to be reactive towards nucleophiles, okay? So you can see there's a charge of a +1 there on this resonance structure. So if you have something that's negatively charged, it's going to seek out that electrophilic carbon atom. So these molecules here we say are electrophiles. They're electrophilic at the carbon because there's a delta plus on the carbon atom and a delta minus on the oxygen. That group there is called the carbonyl, okay? Okay, so whenever you have a carbon-oxygen double bond or a CO pi bond in an organic molecule, we're going to refer to that as the carbonyl. Now let's discuss these three different molecules. Now you see this carbon here, if we draw this resonance structure, has a positive charge, and it looks like that's a secondary carbocation. So let's draw these molecules in here and compare them. So here on the left we have formaldehyde, the one in the middle is acetaldehyde, and I've introduced you to acetone. These are the common names for these carbonyl containing compounds. Now if we were to draw the carbocation here, you would just see that it looks like a methyl carbocation, so that makes this resonance structure even less important. If this was 95% this and 5% that, I can guarantee you that formaldehyde is going to be 99% this and maybe only 1% of the resonance structure, okay? In terms of the overall average contributing towards the resonance hybrid. Acetaldehyde might be somewhere in between. If we draw the resonance structure, there would be a positive charge on carbon. This carbon is bonded to only one other one, so it's primary, okay? This is going to be kind of like a secondary carbocation. As you can see here, I actually have that resonance structure drawn out. So as you move to the right, if you have more carbons surrounding the carbonyl, it's going to stabilize that resonance structure and stabilize the molecule, okay? So if we go this way, all right? It's more resonance stabilized, okay? The rationale there is that if you have more carbons attached to a carbocation, that's going to stabilize the positive charge. So if we have more carbons attached to the carbonyl carbon, it's going to stabilize it, okay? More stable means lower in energy, less reactive. Another thing that we can discuss with these molecules is sterics. So here's formaldehyde. We just have two small hydrogens here, and this green thing is a nucleophile that needs to attack the carbon atom. It can do that very easily because hydrogens are very small groups that don't inhibit or sterically hinder approach of the incoming nucleophile. Okay, here's acetaldehyde. We've got the carbon-oxygen pi bond there. We have one hydrogen and one methyl group, okay? So the incoming nucleophile can still kind of attack this carbon, but you can see how the steric bulk here of this methyl group is starting to slow the ease by which that nucleophile approaches and attacks the carbon, okay? Here's acetone, and you can see how we have two methyl groups here, and it's more sterically hindered towards the incoming attack of the nucleophile, okay? So for electronic reasons, we can say that this is more stabilized. That means lower in energy, less reactive, okay? And in the trend from going from left to right, we can say that there's more sterics, okay? So both of these are used to in argument to support the fact that acetone is a more stable, less energetic, slower reacting molecule compared to formaldehyde. So these are all the reasons, but what you need to remember is that on the left are going to be more reactive. For example, form hydrates very easily, and on the right, these are less reactive. Okay, so these are the stereoelectronic reasons, okay? Sterics and then electronics for the stabilization, okay? So stereoelectronics. All right. So let's talk about the nucleophilic addition reaction. In the book, they talk about a Grignard reagent as an example of something we've seen before. But there are two mechanisms, okay? There's acidic and basic. So there's two categories, and these mechanisms should really be learned very carefully. Not sure how well this is going to erase today, so it might become more and more blurry as we move through the lecture. Well, I'll do base mechanism first. Now, because the carbon-oxygen pi bond is very polar, these are going to be polar or ionic mechanisms that involve charges. So I'll talk about which nucleophiles are basic in a second, but let's just talk about the base mechanism right now. If we have a ketone, for example, and we have a nucleophile, okay, the first step is for this basic nucleophile to attack the ketone and give you the addition product, okay? So the nucleophile adds to that. There's a negative charge on that oxygen atom that then becomes protonated in a second step, okay? So step one is, you're adding the nucleophile. In step two, this might be done in product solvent. It might be acid that you add after the case, okay? Here, let me just add acid, all right, which generally we write as hydronium ion if it's a weak acid. So we're adding H3O plus to this, and we form an alcohol. So again, what we've done is an addition reaction. We've added the nucleophile and we have added hydrogen across the carbon-oxygen pi bond. So the nucleophile always attaches to the carbon and the hydrogen always attaches to the oxygen. In an acid mechanism, the order is reversed, okay? In step 1, we have an addition of the nucleophile, and in step 2, we have a protonation. So I sometimes abbreviate that AP in my courses, okay? So you'll have a long list of reagents, and some of them will say AP. That means that it's basic, and it goes through these 2 steps, all right? For the acid mechanism, it's going to be PA. It's the same steps, but they're reversed now, okay? In my course, whenever you have an acid in the reagents, okay, you're going to use protonation always in the first step of your mechanism, okay? So if you see H+, sulfuric acid, H3O+, something like that, protonate in the very first step of your mechanism, and you can't go wrong, okay? So let me show you how this works. We have our ketone once again, and we have H3O+. And what we want to do here is protonate the carbonyl oxygen, okay? So remember, that's the carbonyl group. This is the carbonyl oxygen, and we're going to protonate that. And now we have a very potent activated electrophile. Maybe the nucleophile just isn't strong enough to attack a neutral ketone. So we've protonated it, we've activated it, it's hyperreactive, and now a moderately reactive or a moderately strong nucleophile will now attack this very well. Okay, so this is your protonation step. And then we have a nucleophile that's going to attack this. Oops. So again, we're doing the same thing. We're adding hydrogen and the nucleophile across the carbon-oxygen pi bond there. Okay, so same thing. These are the 2 basic types of mechanisms you'll encounter in this chapter 20, aldehydes and ketones. Okay? Sometimes you have proton transfers later on in the mechanism, and I won't really talk about that, okay? Now, in the textbook, they have a great little table here that talks about the types of nucleophiles you'll encounter in the course, okay? And it's arranged by kind of atom. You've got oxygen, sulfur, nitrogen, hydrogen, and carbon, okay? Okay, so I've edited out me scribbling all this stuff on the board. This is figure, well, it's not a figure 20.2 in your textbook, okay? We've got oxygen nucleophiles, so we're going to deal with water, alcohols, and 1,2-diols. We've got sulfur, which is, hydrogen sulfide and ethane diethiol. We've got nitrogen, primary amines, secondary amines. We've got hydride, okay? So hydride is the source of nucleophile that's present in lithium aluminum hydride and sodium borohydride. Okay, so we're going to use H-. And carbon nucleophiles are going to be carbanions. R- basically is what we have for these. So a Grignard is a carbanion. This is a Wittig reagent, does some strange stuff, but you can kind of think of it as a carbanion. And this is sodium cyanide, that's Cn-. Where's the dividing point? The dividing point is, it's kind of awkward to talk about amines and how how they react, but they're done with an H+ catalyst. So what I do is I make the dividing line right here. Okay? These use acid catalyst in the reaction. These attack and then protonate afterwards, and these are basic. Okay, so all to the left here are acidic. Okay, they're going to protonate, then do attack. On the right, these are all basic, so we're going to attack, then protonate. Okay, so if you have your textbook, you might make a line right here, and just remember, okay, those are basic things. On the left, oh, okay, I'm sorry, yeah, those are basic things. On the left are all acidic. All right, so that's kind of how I split things up in my class. I know amines are much more complicated in real life, but I just like to be black and white. That's my line. These are acidic, these are basic. All right. So that's chapter 20.4. Let's see here. Oh yeah, we do have a problem in the book. Problem 20.6 says draw a mechanism for each of the following reactions. So I'll do A and B here, okay? In problem 1, we have cyclohexanone. We want to treat that with ethyl magnesium bromide, water, and the products for that are ethyl cyclohexanol, 1-ethyl cyclohexanol. Okay, so this is a mechanism problem, so that means we need to draw all the curly arrows or curved arrows. We want to indicate all the formal charges on each separate intermediate. This is a basic nucleophile. We have a carbanion, which is extremely basic. Okay, so in the first step, we're going to attack. We need to draw out the carbon atoms. We need to draw out the formal charge. We ditch the magnesium, which is a spectator ion essentially, and so you can draw out the ethyl carbanion here. That's going to attack the carbonyl carbon. Electrons are going to swoop up to the oxygen. And we stop there. We want to draw the intermediate that forms from this. So that's the critical carbon-carbon bond forming step. Now that we have the alkoxide, that's going to react with water to give us the neutral alcohol. So we draw the arrow pointing to the H and that bond breaking, and that gives us the target molecule. I'll just draw this going up here. So this is A for attack, this is P for protonation. Okay, you don't need to memorize or label these steps A and P. I'm just putting in there for some students that find it very helpful. The next reaction we have is cyclopentanone reacting with hydrochloric acid. To form this sort of structure. Okay, so HCl is an acid, right? So that's going to use the acidic mechanism. So we want to protonate in the first step. Draw out the bond between the H and the Cl because your arrow needs to include that bond. HCl doesn't have a bond shown, so draw that out. Draw your lone pairs on the oxygen atom, and then draw your arrow. Attack the H, break this bond. That's a protonation step. Okay, we have our protonated ketone here. Now we take chloride, and and that's going to attack the carbonyl carbon in the last step to give us the target molecule. I'll just draw the arrow pointing up to that product, okay? So when you draw these curved arrow reaction mechanisms, don't put more than 2 arrows on a particular structure. Later on, for some advanced stuff, we might see 3 arrows, but don't draw a whole bunch of busy stuff. Draw each intermediate that's formed, and then, that's formed in the curved arrow reaction mechanism. That's it for section 4. Stay tuned for section 5. Thanks for watching.